Good afternoon. The lesson that I've written up for the next 4 weeks goes over some of the fundamental yet important ideas in physics, such as matter, acceleration, forces, velocity, time, potential energy, and energy. And these ideas can be a little complex, despite how fundamental they are, without using a little bit of mathematics to understand how they interact with each other. So what this video is seeking to address is some of the relationships between these concepts and these phenomena within physics. So it's going to mostly go over matter, forces, and energy, and how they're related to each other using a mathematical model, using some of these equations that have been derived long before us from Isaac Newton and other scientists. Now with that, we're also going to be doing a little bit of unit analysis within those so we can better understand what's actually occurring when we refer to these equations, because I know it can be a little bit daunting for some students to just have math thrown in front of them without really knowing what's happening. So with that, let's talk about matter. Everything in the universe is made up of matter, from the atom, which is the fundamental building block of matter, to things as complex as humans, planets, stars. Everything in the universe is made up of matter. Matter occupies space known as bodies. A body is anything that is an identifiable object that contains matter. So for instance, bodies have bodies. This pen could be considered a body. This star, this whiteboard, this can of Red Bull, each can be considered a body. It's an identifiable collection of matter or mass. So every body has a mass associated with it. And that's pretty important to consider when we're starting to talk about forces. So when we write out mass in an equation, we're going to label it simply as little m. When we think about a body or a mass undergoing a change in motion, this is referred to as an acceleration, a change in motion. So when a mass is related to an acceleration, a force is produced. And it's been found that mass times an acceleration, denoted as little a, will produce a force, denoted as capital F, in an equation. Now, let's go into some unit analysis real quick so we can just kind of think about what's going on. So mass is measured in kilograms. I'm going to draw an arrow down, which is symbolized by kg. Acceleration is measured in meters, little m, per second squared. So when we're referring to a force, the unit of force is actually a kilogram meter per second squared, which is kind of a hazy unit to think about. So for simplicity's sake, we call that 1 Newton, named after Sir Isaac Newton, who came up with the 3 laws of motion. Now, let's think about this a step further and talk about gravity for a second. Everything on Earth undergoes the force of gravity. It's what keeps us on Earth. So with that, we all occupy a certain amount of mass, and if there's a force acting on us, that then means that gravity has to be an acceleration, and it turns out it is. Through a series of studies, we've found that the acceleration of gravity is 9.8 meters per second squared. So we can also rearrange this equation to understand the force of gravity. Very similar to the last equation, mass times the acceleration of gravity, I should say, denoted by little g, is equal to the force of gravity, big F subset g. So again, it's going to be the same units because we have kilograms, meters per second squared. This then is a kilogram meter per second squared, or a Newton. And we're referring to the amount of force that is occurring on an object. So each of us is undergoing a force of gravity that is our mass multiplied by the acceleration due to gravity of 9.8 meters per second squared. So to think about this a little abstract, so if you have a bathroom scale and you go and stand on it, it's measuring your weight. However, we all know that if you were here on Earth, your weight would be different than if you were on the moon, yet your mass is the same. Weight is actually just taking into account the acceleration due to gravity. Therefore, when you're actually weighing yourself, you're measuring the force that your body has on the Earth, which is just a small aside, but something interesting to think about. Now, I said we were going to relate forces to energy. And how do we do that? Well, the best way to do that is to start using this idea of gravity and the force of gravity. So if I hold this pen right here, we know that it's going to fall. And we can observe that. It fell onto the table. It traveled a certain distance, though, related to its height. I'd say this is maybe half a meter off the table. And then it fell half a meter onto the table. It started at rest, no movement, and went to movement and then rest again. It underwent an acceleration due to gravity, which we just talked about. But the difference in that is it underwent a change in distance as well, the height, like I said, about half a meter. If we multiply half a meter by mass, so if we do mass times our acceleration due to gravity times the distance traveled, or height denoted by little h, we're going to get something called potential energy due to gravity. Potential energy is the energy that an object has the potential to release. So when I hold it up here, when I hold this pen up here, this is a mass. It is up a certain distance, which is the height, and we know that gravity will act on it should I let go. When I let go of the pen, it undergoes the acceleration due to gravity over a certain distance, and therefore has a certain amount of energy carried with it. Let's do a brief unit analysis of this. We know that mass measured in kilograms, acceleration due to gravity is meters per second squared, and we know that height is a form of distance, and distance is measured in meters. When we do this whole unit again, we end up with kilogram meters squared, because meters times meters is meters squared, over seconds squared. Again, kind of a hairy unit to play with, so we're going to call that 1 joule. With meters being that secondary meter in there, making it meters squared, the deciding factor between that and the Newton. What's really interesting now is when we think about the idea of conservation. In physics, there's tons of conservation. Conservation of matter, conservation of forces, and in this case, conservation of energy. No energy can be created or destroyed. It can be lost outside of the system, but it can't be created or destroyed. That means when I say we have a potential energy, we're going to end up with a kinetic energy, which is the energy of motion, because this underwent a motion. None of that energy is going to be gained or destroyed. It's going to be maintained. So our potential energy is going to equal our kinetic energy. So I'm going to write that out real quick. So our potential energy, which is denoted from gravity, is mass times the acceleration due to gravity times height, which is the distance it travels, equals our potential energy, or PE. But that is also going to be equal to our kinetic energy once kinetics take over. And just to save us some time, kinetic energy equation is 1/2 mass times velocity squared. Now, I know this might be a little difficult to think about at first. Where did the velocity squared come from? We'll address that here in a second. So, we know if we were to relate these two, if we want to know how much kinetic energy occurred to just prove that the conservation of energy is a thing, we have to relate these two equations to each other. On top of that, we could try and figure out what the velocity of the pen is when it falls, without having to take slow motion pictures and analyze it in a photo editing software and come up with these crazy numbers. We can simply derive what it would be knowing the potential energy from this point, because we can measure the distance pretty easily. We already know the acceleration due to gravity, and simply by putting this on an electronic mass, we can come up with the mass for it, most likely in grams and a quick unit conversion, but beside the point. So, through these two equations, we can try and figure out the velocity this pen underwent. So to make this a little less messy, I'm going to erase potential energy, the symbol for that, and erase kinetic energy, and just write this as the potential energy equation is equal to the kinetic energy equation. So mass times the acceleration of gravity times distance traveled as height is equal to 1/2 the mass times the velocity squared. So if we're trying to figure out what the velocity is, we need to isolate the v. In order to do that, there are a few things that we can start with to try and make that a little easier. So this pen is not gaining or losing any mass. It has the same amount of mass when it starts up here as when it falls. So we can actually cancel out our mass in this equation. Now, in some instances, you can't. Think about a rocket or a space shuttle being launched into space. It sheds pieces of it as it flies, which in that case means that there's going to be a different amount of mass contained in that. And so that does play an effect in that, but that's a much bigger concept. But it's an idea that we use this base idea and concept for in the real world, is motion of like rockets. So now that we've shown that mass is the same on both sides for our case with the pen, our equation ends up being acceleration due to gravity times the height of the distance traveled is equal to 1/2 velocity squared. Now, we still need to try and isolate this v. The way we do that is, let's get rid of this 1/2. The way we can get rid of this 1/2 is by multiplying by 2 on both sides. If we multiply by 2 right here, this cancels. And if we multiply by 2 right there, we end up with 2 times the acceleration of gravity times height is equal to velocity squared. Now we're really close to getting this. There's only one thing standing in the way, and that's this squared. The way that we get rid of the squared is to square root it, and that will isolate the v. But we have to square root on both sides. So we square root velocity squared, and we square root 2 times the acceleration of gravity times height, and we end up with 2 times the acceleration of gravity times height square rooted is going to be equal to our velocity. We are now able to figure out the velocity this pen carries with it as it travels without having to get fancy software or anything. We can simply derive it mathematically using 2 very simply measured variables, mass and height. We can then figure out the velocity it undergoes when it goes through the change from potential energy to kinetic energy. Now, there's one more note that I should make about this, and that is, while they're equal to each other because they're conserved, they're not technically equal in the sense that if I move the pen from this height to this height, it's not going to have the same potential energy and kinetic energy the entire time. They're inversely related. As potential energy goes down, the kinetic energy goes up, and vice versa. Think of it almost as having $100 in your bank account. That's your potential energy. Let's say you go out and you spend $10 of it. You don't still have $100 in your bank account. You've used some of it, and it's become purchasing power dollars, right? $10 out, but you still have 90 in your bank. That would be almost the same as this pen starting at this initial height and only going down this far. It's lost about that much. But so that means that this much right here, this distance that it's traveled, is now been transferred into kinetic energy. But we still have the potential energy from this new height to the table. So overall, within it, it's still going to equal out. But at each given moment, it's inversely proportional to each other. So that's something to think about. But hopefully, us going through and looking at some of these equations will help in the future as we go through this unit and start looking at how all of these different phenomena relate to each other, especially as we get to the end of unit project. So thanks for watching. I hope it helped.